Okay, welcome everybody. I hope you had a nice night and are ready for another session. I am Alexander Lex, I'm from the University of Utah, and you are in the Transforming Tabular Data and Grammars session. We have a few exciting papers, and without talking too much, we'll just kick off. We first have two virtual presentations with Q&As followed by that, and then the rest of the talks are going to be like a mix between virtual but mostly in person. Great, so our first talk will be revealing the semantics of data wrangling scripts with comatics, which will be presented by Kai Sean. Okay, let's play the video.
Hello everyone, I'm Kai from Zhejiang University. Today, I will introduce the latest paper from our group, revealing the semantics of data wrangling scripts with comatics. Data wrangling is a non-trivial activity of cleaning, transforming, and enriching data into a designed form. It has become a routine for data workers who carry out data analysis tasks with different levels of expertise. Data wrangling often involves a variety of data transformations, such as sorting, filtering rows, and merging columns. Kisico et al. Structured a multi-table framework for data wrangling, including 15 high-level transformations. A commonplace method of wrangling data is writing scripts in various programming languages, such as R and Python. In this case, data workers usually seek to understand the semantics of wrangling scripts in various scenarios, such as code debugging, reusing, and maintaining. Here, we define the semantics of wrangling code as the type of data transformation and its parameters. For example, the semantics of this line of code refers to sorting the column num of the input table in descending order and returning the output table. A body of prior work has been proposed to help data workers understand wrangling scripts. Some debugging tools are useful for revealing changes in data tables, but they cannot support inferring data transformations. Some tools are designed to visualize the semantics of data wrangling. However, they rely on handcrafted rules to parse code, resulting in poor generalizability and scalability. In this work, we propose a pipeline, comatics, to automatically reveal the semantics of data wrangling scripts by inferring the typesets of data transformations with their parameters. However, developing such a pipeline poses three levels of challenges. First, different scripting languages have diverse regulations in implementing data transformations. For example, there are different ways to represent the descending order in different languages. Second, in one language, there are different functions to implement the same data transformation. Third, some functions may omit important parameters for simplicity. Those challenges hinder novice data workers from understanding the semantics of data wrangling scripts. To address those challenges, we balance qualitative research and machine learning techniques. Specifically, we apply a qualitative method to characteristics or design space of table changes to infer transformation candidates, and leverage a CNN model to resolve ambiguities. We observe that differences between input and output tables can reveal the transformation type to some extent. In this example, we found the second row is deleted, while the others remain unchanged. Thus, the transformation belongs to deleted rows. Further, if all deleted rows contain missing values, the transformation type is likely to be drop NA. Motivated by the observation, we attempt to explore what changes can be made to tables for different transformations. To this end, we first collect a real-world dataset, including 931 lines of wrangling code, where each is annotated with its input and output tables and a transformation type. Here, the transformation type is a combination of one high-level transformation and one low-level operation. We then record the differences between input and output tables and use the qualitative method of open and actual coding on those differences. Finally, we develop a design space for table changes. The design space comprises 4 types of data objects and 5 properties of data changes, totaling 103 characteristics to describe table differences. To utilize table differences for semantics inference, we establish a mapping between transformations and characteristics. For each transformation, we categorize characteristics into 3 groups. After performing a transformation, inevitable characteristics will definitely exist in table changes, where impossible characteristics are the inverse. Possible characteristics are those may or may not appear. After that, we develop semantics, a 3-step pipeline to automatically detect the semantics of wrangling scripts. Semantics first generates intermediate input and output tables for each code and detects changes between them. Then, it identifies the transformation type through 2 components. Last, it infers parameters for the transformation. Let's see the pipeline in detail. Since table changes are conducive to identifying the transformation type, we first execute the wrangling script on given the source table to obtain intermediate input and output tables for each line of code. Then, we detect table changes based on the design space for each pair of input and output tables and generate a set of characteristics. In the second step, we first use a characteristics-based component to infer the transformation type, which involves 2 strategies. Take the first characteristics set as an example. C1 is an inevitable characteristics of T1, but it is not in the current characteristics set, so we filter out T1. As for T3, C2 is impossible but in the set, so we exclude T3. Since there are 2 ambiguities in inferring the transformation type based on table changes, the inference results may not be unique. Therefore, we get a set of transformation candidates. To resolve the ambiguities, we employ a Siamese convolutional neural network to calculate the likelihood of each candidate. Siamese CNN is a kind of flexible classification model that is suitable for few-shot problems and imbalanced data. Here is the architecture of the model. Besides the table changes, we found the semantics of a transformation can be implied in the code. So we take the characteristics, the function name, and its function parameters as input to the model. Please refer to our paper for details. The third step aims to infer parameters for transformations. We first define a set of parameters, namely slots, for each transformation. We then detect those parameters, that is, filtering slots based on the wrangling code, table changes, and input and output tables. Finally, we obtain the semantics of a line of wrangling code. To evaluate the performance and the generalizability of semantics, we designed 5 sets of experiments on our collected dataset. The results show that semantics achieves more than 90% top 1 accuracy. Moreover, we evaluated the flexibility of our pipeline. We apply it to 3 applications in different domains. Let's see the first 2 applications with a video. The first case shows that the semantics augmented Jupyter Notebook can perform code annotation automatically. In the second case, semantics can help solvers to support statements that are not supported in the previous version. In summary, our contributions include a design space for table changes and a pipeline for inferring semantics. In the future, we plan to improve the performance of semantics, enhance its capability, and incorporate it into different applications. That concludes my presentation. I'm ready to take questions. Thank you.
Thanks, everybody. Let's see, are we, hello.
Hello.
Great, so if you have questions, you can type them in Slido and I can read them out, or you're as welcome to walk up to the microphone and ask a question if you'd like. No questions yet. Now I'll get to start us off. You mentioned that you used some example data sets to train, right, as input. But I didn't really understand where you got those from. Were these data sets that you curated yourself, or like the scripts, right? Or did you like find this on GitHub? Can you talk to us a little bit about these data sets?
Okay. I collect our dataset from some open source websites such as GitHub and Cargo and so on. We also apply three criteria to filter some good dataset code from those source data set.
Yeah, okay. Thanks. We have a few questions on Slido now. There is a question from Joe. Do you think your approach could be used to help optimize wrangling steps? For example, replacing fold to filter with filter to fold?
Sorry, I didn't quite catch the question here. Could you please repeat it
your
slower?
Could your approach be used to help optimize wrangling steps?
Maybe it cannot to do so because our goal of the semantics is to help data workers to understand the semantics of data wrangling scripts, but not wrangling help them to rank data.
Okay, thank you. There's one more. I'll do one more question from Slido, and then we'll move on. Can your approach be used to translate R scripts to Python or vice versa? Can you translate between programming languages?
I think we anticipated to do so. I think our work can be applied to the source-to-source compiler, in which case we can transform wrangling code, which is written by R language, to be translated to another language, such as Python. Because semantics can act as an connector, it can connect two languages, which can wrangling code, which can do a single transformation. I think our work can be applied to the source-to-source compiler in the future work.
Okay, great, thank you. So Kai is taking a short break because the next paper is also by him. So we'll be listening to the next video first and then have him back for questions again. Thank you.
Thank you. Hello everyone, I'm Kai from Zhejiang University. Today, I will introduce the latest paper from our group, visualizing the scripts of data wrangling with SOMAS. Data wrangling is an arduous process of transforming, reformatting, and integrating data to make it more palatable for miscellaneous downstream purposes, such as visualization and analysis. Data wrangling often involves a number of data transformations, such as filtering rows, merging columns, and sorting. Texaco et al. Structured a multi-table framework for data wrangling, including 21 transformation operations. Nowadays, numerous scripting languages with their data manipulation libraries have been commonly used for data wrangling. At the same time, data workers usually seek to understand the semantics of scripts in various scenarios, such as validating the process of data transformation to ensure accuracy, and learning the idea of data wrangling for reusing. However, understanding scripts requires advanced programming skills, and the process is time-consuming. A number of program visualization techniques have been proposed for debugging and communication, but none of them are proposed in the context of data transformation, which aims to reveal the evolution of tabular data. Data provenance records the history of changes during analysis. Several tools leverage animations to visualize the provenance of tabular data. Animation is useful for communication. However, it is hard to explore and control. Besides, those tools focus on presenting the provenance of a single table. In this work, we design and implement a pipeline, SOMAS, to visualize the semantics of code pieces in the context of data transformation. SOMAS accepts a data wrangling script with its source tables as input and results in a glyph-based provenance graph, where nodes represent tables and edges denote data transformations. In order to help data workers understand and communicate a data wrangling script, we conducted several rounds of interviews with data analysis to iteratively extract design requirements. Guided by the requirements, we first explore design space of glyphs for depicting individual data transformations. The design space consists of two primary dimensions, namely the type of parameters and the potential visual channels. After examining 160 functions used for data transformations, we categorize 6 key parameters that should be mapped to the visual channels. Take the line of code as an example. The unite is a function name that reflects the transformation operation it targets. Table 1 and Table 2 are the input and output tables of the function, respectively. Those columns are explicitly mentioned in the function. The separator is one of the transformation parameters. And column 3 is a contextual column that is not involved in the data transformation. Besides, we also consider implicit columns or rows which are involved in a data transformation but not explicitly mentioned in the function. We use the table metaphor as the fundamental structure of our glyphs. Each glyph contains 3 main parts, namely an input table, an output table, and an arrow indicating the transformation. We explore possible visual channels for our glyphs to encode the 6 parameters, including input in table text, out table text, cell color, and some other considerations. Based on the design space, we derive a glyph collection to depict 23 types of data transformations. Here are 15 of the 23 glyphs. After that, we develop SOMAS to visualize the semantics of a data wrangling script. The architecture of SOMAS consists of 2 major modules: the program adapter and the visualization generator. Program adapter aims to generate a series of transformation specifications. It contains 3 steps. First, program execution uses a corresponding language interpreter to execute the script. This step can obtain input and output tables for each function, which helps to construct the provenance of tables. Then, code parser will pass each line of wrangling code into 3 paths, namely the variable names of input and output tables, the function name, and the function parameters. Last, we craft rules to infer the transformation type of the line of code based on the results of the above 2 steps. After passing all lines of wrangling code and deriving their transformations, program adapter generates a specification for each transformation. Then, the visualization generator will construct a data provenance graph by utilizing those specifications. The nodes of the graph are data tables, and the edges are data transformations. We depict useful information in each node, including where the table is created, the table name, and the size of the table. According to the number of input and output tables, we categorize edges into 3 types, namely coverage edges for many-to-one table transformations, divergence edges for one-to-many table transformations, and directed edges for others, like one-to-one table transformations. Finally, we depicted glyphs aside from each edge in the provenance graph to present the detailed semantics of data transformations. To assess the effectiveness of our visualization designs, we conducted a user study centered on 2 high-level questions. We designed 5 function understanding tasks and 5 script understanding tasks to answer the questions respectively. We compared our visualization design with textual descriptions derived from Trifactor. We recruited 20 subjects to conduct the user study. The results show that participants achieved better accuracy with less time using SOMAS and preferred it over textual description. Besides, we implemented 2 prototypes to demonstrate how SOMAS can be applied to different usage scenarios. Here, we introduced the 2 prototypes with a video. SOMAS is implemented as a web-based system which has 4 panels. The data panel allows users to upload their input tables after selecting a programming language and copy-pasting a piece of data wrangling code to the script panel. Users can click on the Run button to get provenance displayed in the graph panel. Users can zoom and pan the graph to switch between an overview and a detailed view of the individual transformations. Besides, users can click on one node, and the table panel displays the detailed table. Similarly, when clicking on an edge, its function in script panel is located and highlighted, and vice versa. Users can modify the code and run it again to see how the code affects the transformation results. We also apply SOMAS to explain scripts generated by morphers. Assume Devin has 2 original tables and 1 target table at hand. He first uploads those tables to the system to understand how to transform the original tables to the target table. After clicking on the Upload and Run button, a piece of code is shown in the script panel, and a provenance graph is displayed in the graph panel. Devin sees 7 edges from the provenance edge, indicating that the entire process takes 7 data transformations. In summary, the contributions of the work include a design space of glyphs for depicting data transformations, a pipeline SOMAS for visualizing data wrangling scripts, a controlled study, and 2 example applications. In the future, we plan to enhance SOMAS by supporting more various functions and explore how to visualize conditional statements and loops. That concludes my presentation. I'm ready to take questions. Thank you.
Thank you. Great, there's one question on Slido, and I'm going to keep it to this one question because we're running a little bit short on time. The question is, what do you think are the trade-offs between visualizing the provenance as a directed graph and as an animation?
I think animation, I acknowledge animation is helpful to help data workers to understand the semantics of data wrangling scripts, but I think it is so hard to control and focus on what I'm interested in the process of individual data transformations. While in the graph, we can pan and zoom, we can support a lot of interactions on the graph. So I think it's helpful for data workers to interactive explore the graph, explore the visualization with between visualization and the code. Maybe it can help data workers understand the semantics more conveniently.
Great, thank you. There's a few more questions on Slido, but maybe you can answer them on Discord. And so I want to thank Kai again for doing 2 talks in a row remotely, and hand it over to our next talk.
Thank you.
Come on up. Great. So our next talk will be presented by Ran Chen and Xinhua Xu, who will be talking about Rigel, transforming tabular data by declarative mapping.
No HDMI. Hello everyone, welcome to my talk. I'm Xinhua Xu. Today I will introduce our work, Rigel transforming tabular data by declarative mapping. So in the process of data analysis and decision making, we need to transform raw data into different columns, different consumable forms for analysis. However, the transformation process can be very difficult for users and might occupy up to 80% of the time in the whole process. So traditionally, users will write custom scripts and apply data operations to transform data in batches. However, this approach can be challenging due to the considerable time and efforts required. And also, these scripts are mostly tailored for a specific data set. That means it cannot be easily generalized to other scenarios. And recently, we see interactive systems have emerged to make data transformation more accessible to a broader audience. For example, we see here the stepwise recommendation system. They can suggest operations for subsequent transformations. However, we may find it may lead to the lengthy and multiple operations in complex tasks. So to address this issue, some systems proposed a by-example approach, which can synthesize multiple step operations and recommend transformation procedures based on the input examples. For instance, here we see the example is to concat the authors of a paper into a cell. However, this approach may not always work well. We see that the system can misinterpret users' intent due to the ambiguous examples. For example, here we see now we expand the test data with more records. The transformed data does not output the correct results, as the system wrongly interprets the intention is to concat the first 3 authors. So the newly added author is placed in the single cell here. Also, this approach assumes that the users should have a clear transformation goal in their mind. That means it may impede an open-ended exploration. So how can we design an interactive system that can preserve these strengths but can address the issues by disambiguating examples and also supporting the exploration of diverse transformation results? So in this work, we introduce RIGO, a general data transformation system that can incorporate a new declarative mapping approach. There are two parts. I will begin with the underlying declarative mapping approach first. We developed this approach with an aim to formulate the user intent into unambiguous table examples. So specifically, we will formulate the table as a visual arrangement of interrelated data in a column and row form. So based on this idea, we divide the table into 3 channels, including row, column, and cell. And then we model the data transformation procedure as specifying the transformed target table by mapping the form from the import data tables. And we also allow a set of operations to be applied to obtain new channels. Now let's see a concrete example. How we transform the two import data tables into the tagged data tables using our approach. And each row in the tagged table shows the abbreviation of the state, and each column represents the year, while the blue cell here represents the formatted GDP values. Now, let's construct the specification. First, we see the row of the tagged table is derived by splitting the column of the state abbreviation. And then the column is unioning the year columns of the two import data tables. And finally, the cell is a formatted GDP value of the import data tables. So based on this specification, we explain how this approach works. It first extracts the data variables and their relations by scanning the whole import data. And then we map the data variables to row, column, and cell channels, as well as their data operations to compose the desired tables. And this step should be done by users through the interactions with our system, because they need to demonstrate their intent of the transformation. And finally, we search and places data values into the corresponding cells based on the relations to produce the tagged tables. So after knowing the underlying declarative mapping approach, we introduce how the RIGO system works. So it's an overall pipeline where RIGO allows users to construct the mappings by dragging or typing values from the input data into a tagged spreadsheet. And then the RIGO recommends possible mappings from the data to table channels to declaratively compose user desired tables. We then see how it actually performs in our system. So the top left raw table, users can click the derive button here to apply operations and derive new variables. And then users can directly drag data variables to table channels to construct the tagged table. Or they can drag or type some values from the import data. But at this time, we found that they need to disambiguate their intentions in the right side suggestion views. They should specify the mapping from the import to the tagged tables. And finally, to support the open-ended exploration, the suggestion view will recommend alternative table shapes and variations by adding unused data variables. So it also supports the hovering to preview the effects in the bottom side. And you can find a complete and complex usage scenario in our supplementary video. Finally, to evaluate the RIGO system, we cover 20 out of 21 transformation operations from a state-of-art data transformation taxonomies. And you can find all these examples at our observable page. And we also conduct a user study to evaluate RIGO. We recruited 12 participants, and they are required to conduct 4 transformation tasks using our system RIGO and the baseline system FUFA. We choose FUFA because it is one of the state-of-the-art by example recommendation system. And also it provides smooth interactions instead of asking users to write their program scripts. So we collected 3 metrics in the user study: time and the number of mouse clicks and the keystrokes of each task. Overall, we found that participants successfully completed more tasks with less time and fewer mouse clicks and keystrokes in RIGO than FUFA. When inspecting the failures, we found that the fails in FUFA may be due to the overly simple or complex examples the users are required to provide to the FUFA system. So the system might wrongly interpret these examples and produce the wrong results. And we also see some failures in RIGO. And during the interview, we found that users said they may not familiar with the by mapping approach and also some interactions provided by RIGO. So the qualitative feedback shows that the RIGO's advantages in helping open-ended exploration and transforming the data from the overall logics of the tables. And also it can help reduce the gulf of evaluation. To conclude, we introduce a declarative mapping approach and develop RIGO to support expressive and efficient data transformation. Both the RIGO system and our declarative mapping approach are open sourced at GitHub. And you can find more work on my personal homepage, and I'm on the job market looking for a postdoc position. That's all. Thank you for listening. I'm happy to take any questions.
Thank you very much. So we have one question from Cameron Yick. How do you sort the different recommendations for next step transforms when supporting data exploration?
Yeah, actually, we think there are 2 directions. One is that we may develop more packages for scripts to transform the data tables. And one is that we need to allow the general users to conduct some transformation tasks because there are many data analysis tasks in the world. We think our approach is we allow users to construct their mappings from the overall logics of the table shapes. So yes, we think this one can be our further step to by example approach because they are from the fine-grained aspect. Yeah.
Okay, great. Thank you. Let's thank our speaker again. And we'll any follow-ups on Discord, please. And we'll move on. The next presentation is going to be virtual again. We have high transformation and visualization for hierarchical tabular data presented by Guzeng Li and Runfei Li.
Hi everyone, I'm Runfei Li from Beijing Institute of Technology. Today, I'm excited to share our work Tabular, an interactive transformation and visualization approach for hierarchical tabular data. Tabular data has been a critical data management approach and is widely adopted by many application domains. We focus on tabular visualizations, which either encode a data item within a cell or integrate visualizations for a block containing multiple cells. However, most of the existing studies about tabular visualizations only focus on simple flat tables, but ignore those hierarchical ones. Hierarchical tables refer to tables with a multi-level heading structure. They are widely used and have a better capability of efficient data management. However, hierarchical headings also build incompatible logical and positional relationships between data items. First, cells with the same relative positions might have different relationships. In addition, some closely related items may not be adjacent to each other. These problems pose some challenges for creating tabular visualizations. First, to create high-quality visual representations, users need to specify several discrete blocks, which is tedious and time-consuming. Second, to allow exploring tabular data from different viewpoints, users need to frequently change the position of cells to place associated cells adjacent to each other. To address the above challenges, we present Hightailor, a technique to support interactive transformation and visualization for hierarchical tables. Hightailor consists of 4 panels. The tabular visualization panel shows the original data and the embedded visual forms. The transformation operator panel includes 6 different transforming operations. The visualization template panel displays a wide range of visualizations that we support creating. The visualization configuration panel shows the parameters of visualization which support user modification. Now let's talk about the pipeline of Hightailor. First, users can upload a hierarchical table and Hightailor will parse its headings and construct an abstract model. Then users can transform the table by direct manipulation. After that, users can select a specific table unit and Hightailor will recommend other related ones with different priorities. By setting the priority range, users can determine a series of targeted table units and create visualizations for them. In particular, the visualization authoring is an iterative process. Finally, users can interactively explore the visualizations and export the results as images. The detailed techniques of Hightailor consist of 4 parts, including abstract model, hierarchical table transformation, table unit recommendation, and table unit visualization. A table is a collection of items which can be divided into entries and labels. Entries are the basic data items, and labels are the attribute values in row and column headings. The abstract model consists of 2 parts. The first part is about the relationships between labels. We define biclusters and hierarchies to describe the relationship. If the labels in a child layer are identical, they are defined as a bicluster. Otherwise, they are defined as a hierarchy. Let's take this table as an example. The second layer of the column headings are the same, so we define it as a bicluster. Conversely, the row headings are defined as a hierarchy. The second part of the abstract model is about the associations between labels and entries. An entry in a table can be located with its row and column locator. We use a label sequence from the first layer to the last layer to describe these locators. For example, this cell can be described with its row locator and column locator, as shown in the picture. We identify 6 hierarchical table transformations, including swap, transpose, to linear to stacked, fold, and unfold. Swap enables analysts to change the order of 2 adjacent levels. Transpose supports swapping between row and column headings or exchanging their position. To linear calculates some statistic values for corresponding data items of all nodes in the same bicluster. To stacked, on the contrary, allows users to discard these derived attributes from hierarchical tables. Fold flattens hierarchical tables by converting one row into multiple rows and folding the set of columns together into one column. Conversely, unfold unflattens hierarchical tables. Next, let's talk about table unit recommendation. Table unit is a cell or block specified by users in the hierarchical tables. The decomposition of a table unit is shown in the picture. We regard a table unit as a primary component for tabular visualizations. To prevent users from repeatedly selecting multiple table units and specifying the same visualization configurations, it is necessary to recommend related table units. We define the priorities of table units to generate recommendations automatically. The priority of a table unit is based on both its row priority and column priority. We designed 2 methods to calculate the priority, including topology-based and name-based. Users can choose a method to compute the priority and select the priority range. Then Hightailor will recommend related table units. In this picture, A shows the topology-based method, and B shows the name-based method. C and D show different table units for recommendation according to their priority range specified by users. Here is a demo for recommendation. Users can modify the recommendation method and priority range in the configuration panel in order to get different recommended table units. After selecting and recommending table units, users need to create visualizations and embed them into hierarchical tables. We choose several visualization templates and divide them into 4 categories: unit visualization, data overview, trend tracking, and correlation exploration. Unit visualization visualize the value of each cell, making adjacent cells more comparable. Data overview is designed to show the value of all cells within a table unit. Trend tracking enables users to understand the variance along the row or column. Correlation exploration is used to explore the correlations between multiple rows or columns within a table unit. We validate the effectiveness of Hightailor through a case study. The use case is based on the game hardware sales dataset from VG charts, which consists of manufacturers, console names, sales regions, quarter and months, and years. First, we apply swap and linear to the original table to get the overall sales of each console. Then, we try to create visualizations to help gain some insights. We create horizon graph for all the sum values to show the variance of overall sales over time. After that, we analyze the sales of different products in different regions using unit visualizations. We also generate box plot to explore consumers' purchasing behaviors. And radial plot is used to show the sales proportions of each console among different regions. We also conducted a user study to compare between Hightailor and Tabular. First, the participants are asked to perform 2 tasks using Tabular and Hightailor and record their time of completion. The figure shows that Hightailor is faster than Tabular in both 2 tasks. After that, we asked the participants to rate Hightailor from 7 different aspects. The result shows that Hightailor achieved satisfactory results overall. To sum up, the main contributions of Hightailor include 3 parts: an abstract model, a series of recommendation methods, and a prototype system. In the future, we intend to improve our work in scalability, evaluation, and visual encoding consistency, and try to explore more intelligent tabular visualization techniques of hierarchical tables. We are really excited to share this work with you, and you can find more information on our website. Thank you for listening. Hi, everyone.
Thank you. Hello.
Hi.
Great. So we have 2 questions on Slido. The first one here is by Jesse. How did you determine the transformation space? Why did you finally choose those 6 operators?
Okay, I think that is a good question. And first, I want to make it clear that our purpose is to solve incompatible logical and positional relationships in hierarchical tables for transformation. So we want to create high-quality embedded visual forms. And then we try to follow the principles that we choose the operations either because it helps to change the relative position of related cells, or maybe the operator can help us generate new cells like mean values, which can be taken as references. So in a word, our transformations may not cover all the possible ones in hierarchical tables. We just choose 6 typical ones that can better facilitate the creation of tabular visualizations. And maybe in the future work, we'll consider about enriching the transformation space for other research purpose. Thank you.
Thank you. Well, let's thank Ronfei again and move on to our next presentation. So thank you very much.
Okay.
So please go ahead. So this is kind of, we've wrapped up the tabular data wrangling part of this session and moving on to our grammars part of the session. First paper in the series is going to be Animated Vega Lite, Unifying Animation with the Grammar of Interactive Graphics, which will be presented by Jonathan Song and, what was your name? Sorry. It's Josh Pollock. Thank you very much.
Hi everyone, my name is Jonathan Zong.
And I'm Josh Pollock.
And we're excited to present our work today on Animated Vega Lite, Unifying Animation with a Grammar of Interactive Graphics.
So consider these three versions of Gapminder: one static, one interactive, and one animated. These graphics show identical information, but they afford different levels of clarity, time commitment, and visual interest. During rapid prototyping, switching between these different chart types can allow an author to create a suitable explanatory graphic or uncover different kinds of insights in their data set. But while these graphics have similar semantics, we specify them using very different abstractions. In static charts, we use the concept of faceting. In interactive charts, we use event streams and data queries. But in animated charts, we use keyframes and transitions between them. And these independent abstractions yield a highly viscous authoring process because switching between each of these charts means translating your intent between different concepts. We present Animated Vega Lite, an extension to Vega Lite that supports rapidly moving between static, interactive, and animated graphics using shared abstractions.
To show how Animated Vega Lite affords rapid prototyping across these different modalities, we'll walk through an example usage scenario involving a bird migration data set. Let's say you have a data set with birds' locations at different days throughout the year. To get an initial overview of this data statically, you can visualize each migration path as a line, with lines colored by bird species. This can be a bit visually overwhelming, so you might start out by adding some interaction. So to add a hover interaction in Vega Lite, you can define a selection that's populated on mouse over events, and it selects the current species of bird you're hovering over. Then you can use this selection to drive some conditional encodings on opacity and size so that your selected data stands out from the rest. And finally, you can add a tooltip encoding to show the species name on hover. So far, this is all standard Vega Lite. The static and interactive views help give an understanding of the migration paths, but it's harder to figure out from just the line where birds are at specific times. Viewing an animation of species location over time can help surface different insights. So to make an animation version of this visualization, we start by changing the mark type from line to circle. And then we create a new time encoding, which maps the day field to a time range, which we specify here to be 10 seconds. And that's all we need to create this animation with Animated Vega Lite. Implicitly, Animated Vega Lite implements time encodings as selections that respond to a timer event, which drive a filter that represents the data in the current animation frame. If we want to enable more complex animation behavior, we can explicitly write this selection out. For instance, we might want to add trails to each point so that we can visualize some information about the bird's movement along a path. To do this, we add another selection representing the trailing points. And we do this using a custom selection predicate that we've specified to include the trailing 20 days. Now, instead of filtering to only the birds at the current time, we use a filter to show all points within the trailing window. Then we can use a conditional encoding to show the current point at full opacity and the trailing points at less opacity. Now, to bring it all together, we can bind our animation selection to a slider that lets us interactively control the playback of the animation. We can also add back the hover interaction from before to inspect the trails in each frame. So the takeaway from this usage example is that these shared abstractions for static, interactive, and animated charts afford a low-viscous authoring experience.
So how did we go about designing such a system? One of the key inspirations of our approach was a comparison between Yi et al.'s 2007 taxonomy of interaction intents and Heron Robertson's taxonomy of animation types from the same year. We found that the kinds of visualization techniques they referenced, like filtering, panning, and zooming, significantly overlapped, even though the taxonomies characterized them slightly differently. This correspondence led us to the design of animated Vega Light's core abstractions. The key idea of animated Vega Light is to model time in two different ways. First, to integrate animation with static charts, we can think of time as an encoding channel. And second, to integrate animation with interactive charts, we can think of time as an event stream. First, let's explore time as an encoding channel. Returning to the Gapminder example with this concept in mind, we can think of the static version on the left as facetting out years in space, while the animated version on the right facets out years over time. Now, how does that translate to the grammar? Well, by simply changing the facet encoding channel to a time encoding channel, we can switch from producing spatial facets to creating data-driven keyframes. We've thus reduced the complexity of switching between these charts to a single atomic edit. Now let's turn our attention to the event stream model. So if we compare these two Gapminder illustrations, we can see that in the chart on the left, the year field is driven by a user using a slider. And on the right, the year field is driven by a timer. So the difference between the interactive and animated charts is whether a user is causing the data to change over time or the system is. At the level of this grammar, this looks like changing a user-driven event, such as a mouse over event, to a system-driven timer event. And in both cases, these events are translated into data queries that control the rendering of the data set at any given time. So just as in the static case, by generalizing existing concepts in Vega Light, we're able to reduce the effort of switching between these charts to a single atomic edit.
Animated Vega Light adds very few new language constructs. Its abstractions are designed to compose with Vega Light's existing constructs. Many of our examples show the benefits of this composition. Because animation and interaction both use selections, any dynamic behavior that can be driven by an interaction can also be driven by an animation. For example, we take this classic example of an interactive chart and turn it into the equivalent animated chart by changing the event type from drag to timer. To explore our coverage of interaction and animation techniques, we took this idea and applied it across different chart types. And I want to highlight one surprising example we noticed, which is that although these two examples, Gapminder and the bar chart race, look pretty different, because of the way Vega Light composes mark types and encodings, these examples have essentially the same spec. The main difference is changing the mark type and the data, and the scales and transitions are inferred automatically. Coming back to the interaction and animation taxonomies, we found that our examples cover most of the categories in both taxonomies. We are unable to support animations that involve changes to encodings over time. So for example, converting a scatter plot to a bar chart. This is also a limitation of the original interactive Vega Light.
To better understand the strengths and limitations of our tools, as well as how animated Vega Light sits in the larger design space of animation grammars, we adapted the critical reflections evaluation method from Satya Narayan and others. Specifically, we recruited expert designers of 4 other animation grammars to deeply engage with our system, and we conducted semi-structured interviews before and after they used our tool. We had 4 main findings from the study, but in the interest of time, we'll only cover one of these, scene versus segue dominant abstractions. And we really encourage you to read our paper to learn more about these other things we discovered through this process. The idea of scene and segue actually came from Thomas Lynn Peterson, one of our participants, who's the architect of GG Animate, and he introduced these terms in 2018. Simply put, a scene animation is one where data changes over time, but the encoding is fixed. And that's like Gapminder on the left here. On the other hand, a segue animation involves transitions between different encodings. The example on the right involves changing a bar chart to a scatter plot and was inspired by the R2D3 article on machine learning. We found we could fairly cleanly split animation grammars into one of 2 categories based on whether they better supported scene or segue animations. And to see why that might be possible, notice that scene animations tend to rely on data-driven keyframes where each keyframe has the same encoding. And scene-dominant grammars such as ours focus on automatically generating keyframes while keeping transitions relatively simple. On the other hand, keyframes and segue animations are highly customized, and each one may have a different encoding. In segue-dominant grammars, users typically provide keyframes as individual charts or SVG files, and it's the system's responsibility to provide advanced support for transitioning between these highly customized keyframes. But we also found that the distinction between scene and segue isn't always so clear. For example, this swimming world records example from Data Animator looks like a scene animation because it has a fixed encoding. But in fact, the authors of Data Animator expressed it using a start and end keyframe and then specifying a data-driven transition between the two keyframes. So future work could explore how to blend scene and segue dominant abstractions. Finally, we plan to contribute back to the community of data viz practitioners by merging our animation grammar into the main Vega Lite open source project so that everyone can enjoy making gapminder animations and bar chart races. We hope that animated Vega Lite can facilitate future research on interactive and animated visualizations akin to the role the original Vega Lite has played. For example, by helping researchers study mixed interactive and animated charts. Thanks.
Thank you. We have a few questions on Slido. The first one is, regarding the conversion of static facets to keyframes, how coarse or fine should the keyframes be specified? What effects does the level of granularity have on the quality of the interpolation?
That's a great question. So we are interpolating between the keyframes when we do time encoding, at least in our prototype compiler. And I think the main consideration here is that the keyframes need to be evenly spaced for a smooth animation. So for example, if you have in your data, one set of rows has like year equals 1985, and then you're jumping to like 1990 and then 1991, those will kind of get interpolated with a fixed duration, so it might not actually reflect the meaning of the data.
Great, thank you. I'll take one more question here. Is there support for different sorts of easing functions or other types of animated interpolation? Those seem like important concepts for authoring animations, but don't have nice analogs for faceting and interaction.
Yes, so we do include some discussion of easing in our paper. The main consideration here is whether to apply easing globally over the duration of the whole animation or to apply it in between each pair of keyframes. And I think for the purposes of merging into Vega Lite, we still have some design consideration to give to that, but there's some discussion in the paper on that.
Okay, well, let's thank Jonathan and Josh once again. There are a few more questions which I'm hoping you guys can respond to on Discord. And then the last talk of our session is going to be given by Andrew McNutt. No grammar to rule them all, a survey of JSON-style DSLs for visualization.
Hi. The use of JSON-based languages is an increasingly common means of expressing visualizations. These structured domain-specific languages are expressive, enable rapid domain exploration, and are richly portable. These, among other benefits, have caused the languages to be quite popular, with Vega and Vega Lite enjoying millions of downloads per month and influential, with a large number of languages following the practices developed by those DSLs. Their form falls into an interesting intersection between one that is easy for end users and one that is easy for automations. On the end user side, JSON languages are approachable by motivated domain experts, but can lack some usability tools found in more general languages. The exchange for this usability, then, is that such languages are trivial to mechanize, which can allow for advanced tools like recommendation and automated guidance. Despite this popularity, there's been little study of the design and implementation patterns of these languages. Wang Sapasawat developed a taxonomy of web-based visualization libraries, which includes, but is not limited to, JSON-style DSLs. while Pu and friends held a special interest group at Chi 21, visualization grammars, which highlighted the lack of a coherent definition of and evaluation mechanisms for visualization grammars. While these efforts are important, they leave open questions about what design and implementation patterns are used in JSON-style DSLs. So, to answer these questions, we conducted a survey of JSON-style DSLs and then refined them into a suite of design concerns. Through these efforts, we seek to provide a coherent view of this space so that future language designers can be better aware of the available choices and trade-offs, as well as opportunities in this space. We conducted our survey in a fairly standard way. We searched various academic search engines, traditional search engines, and code repositories using a variety of search terms and snowball sampled as applicable. We included a language if it uses standard serialization language, produces a visualization, and is usable by a human. Our survey yielded 57 distinct languages, ranging across sources, topics, domains, and a wide variety of other characteristics. This includes familiar languages like Vega and Vega Lite, as well as more specific ones, such as the Neo-Confusion Matrix language, the unit visualization language Atom, the VR charting language DXR, as well as She and Friends scientific visualization pipeline language. To better understand these languages, we also collected representative examples of each language, yielding over 4,000 example programs, which we collect as a DSL zoo. This collection allowed us to more easily analyze the corpus compared to merely reading the documenting papers or descriptions. To better understand what we found, we coded each of the discovered languages along a variety of axes. We iteratively added, removed, and adjusted categories until a theoretical saturation was reached, from which we identified 5 key concerns or themes. Time is short today, so we'll forgo discussion of the top 3, domain concerns, affordances motivated by identification of the end user, and practicalities of where work is done. Instead, we'll dive more deeply into the other 2. So, in models, we ask, just what is this DSL? Every programming language has a conceptual model of what is happening in response to input from the programmer. We observed that languages tended to either be high level, in that they were close to the language and logic of the relevant domain, or low level, where they were close to the rendering context. In addition, we noted that they tend to either be formal, showing that they have some structural pattern that informed what language designs were allowed, while others were colloquial and used an ad hoc language definition. There were examples of each combination in our survey, but we show some here. While the difference between high and low level is important and interesting, today we're just going to focus on the formal colloquial divide. On the formal side, you have many languages that are backed by a rigidly defined conceptual model, while on the colloquial side, you have those that are defined without an underlying structure. Each are useful, but have different benefits and weaknesses. Formal languages have the power to simplify intent and allow for fluid exploration of domain by removing design pathways that are irrelevant to the model. Many of these follow Wilkinson's grammar of graphics to rich effect, like think how big Vega and Vega Lite are. Interestingly, Wilkinson repeatedly argued that his was the only grammar of graphics. However, languages are always local to their domain, and if there's to only be one visualization DSL, then it will be trivially poorly matched to tasks not modeled. For instance, Wilkinson's grammar of graphics and nearly every instantiation of it has poor support for mixed data and non-data tasks like annotation, data-driven layouts such as tree maps and cartograms, and just elements outside of its conceptual model. Other models reduce their generality to handle some of these issues. For instance, Atom uses an L-system-inspired partitioning model that enables rich expression of unit visualizations, but at the cost of general charting power. At the other side of the spectrum are colloquial models. These models are sometimes overlooked or even looked down upon by us, the academic community, despite their ability to adapt to and accommodate real-world situations and problems. For instance, only 4 DSLs in our survey provided their own accessibility features. The dearth of features like accessibility or annotation is likely because those features are not modeled or would be difficult to model, and so are either left out as implementation details or the end users asked to sort of hack and slash them in. Colloquial models, in contrast, can simply just add these things because they're not beholden to an overarching model. That said, colloquial models are typically ad hoc in their design, and so their interfaces can be harder to learn or to operate. For instance, a conceptually related but graphically distinct chart might require an entirely separate syntax under such a model. In exchange, though, more esoteric charts, such as cartograms, are easier to make. Developing a better understanding of these forms and the way that they are used by system designers and domain experts is intriguing and important work, especially in light of their decades-long popularity of the specification style. I argue that, as researchers and toolsmiths, we should endeavor to meet users where they are, which may mean working to enrich colloquial models rather than merely formal ones. Finally, let's turn to relationships. Languages rarely exist in a language vacuum. So, for instance, languages like Python include a syntax for regular expressions that's fundamentally unrelated to their own. The DSLs in our survey are no exceptions, and we have identified 3 major patterns of DSL relations. In compilation, code is generated that is processed by another entity. This has the benefit that the language gains all the features of the compile target, such as rendering, data manipulation, or other thorny UI elements like tooltips, but at the potential loss of domain awareness and enforcement of the shortcomings of the target. For instance, Vega Lite struggles with texture encoding because its compile target, Vega, doesn't support them. Another prominent pattern is wrapping or embedding, in which another language is embedded either on the language surface or as part of the runtime. For instance, this familiar pattern can be seen with embedding of regexes into Python. It can be good to use the right tool for the right job, like why reinvent Vega Lite syntax for charts when you can just use it? But it also may lead to a language cacophony, which is a well-known error mode in which too many DSLs overwhelm the end user. Finally, many languages extended or contracted another DSL. For instance, GNOME-SPY extended Vega Lite to genomic data, which allows for domain-specific ideas, like genomic coordinates. This can come at the price of needing to write a custom renderer or other custom elements. Valuing composition as a first-class design element in this form of DSL opens lots of opportunities. One such opportunity are compile towers. Visualization systems have a long tradition of re-implementing every single part of the visualization pipeline. And while this is sometimes necessary, again, Vega Lite doesn't support GNOME-SPY's genomic coordinates very well. It's often done needlessly. So it may be beneficial to pay closer attention to the space of available compilation targets such that new languages are added atop this tower rather than reinventing the wheel. For instance, Vega Lite does not handle Gantt charts DAG data very well at all, requiring substantial manual effort to produce such charts. A Gantt chart DSL then might address this by standing atop Vega Lite via embedding of relevant calculations as part of the compilation process and thereby gaining rendering and tooltips without losing domain specificity. The central downside then would that error message would be produced in Vega and would be irrelevant or confusing to a Gantt chart user. As with every aspect of DSL design, there is no one golden approach. Everything is a trade-off, and for relationships, that tension comes down to an exchange of customization versus reuse. There's a ton more to say about the rest of these elements, and you should go read the paper if you're curious about them, but I want to highlight a couple opportunities in this space with the time I have left. A key value of these languages is that they are machine operable. So it's a missed opportunity that almost no DSLs that we surveyed allowed for specification of programs through a mixture of direct manipulation and code. For instance, tasks like annotation often require pixel precision, which can be tedious to specify in code and is more naturally specified through direct manipulation, whereas more abstract tasks like mapping of columns to encodings may be better suited to text. If this project has demonstrated anything, it's that there will continue to be visualization languages developed. Some of them may even be in the JSON style. We believe that this is a positive trend and that there should be more such languages. More chart-specific languages, like for hot plots, Gantt charts, sets, or graphs. More task-specific languages, like for text analytics or for time series. More medium-specific languages, like a grammar of sonification. More languages that cover more specific data types, interactions, and just everything else. There are many tasks, and no one particular language will be able to capture all of them without compromising the utility of its design. That is, there will be no grammar to rule them all. Thanks for your time and attention. I'll be happy to take any questions, and I'm on the academic job market looking for professorships in North America. Thank you.
Thank you. While you have a second to type your question, I'll ask one. Which of these opportunities would you personally want to take up next? Which grammar do you want to write yourself, or would you be most excited about?
All of them. No, I really want bidirectional languages so bad. I really hate having to switch modalities of sort of reading and writing to get things done, and I think that's a really good first step. Something I had in the slides but dropped, another opportunity I think is really important is developing a semantics of visualization grammars. We have a lot of formal syntaxes, we write down what statements are allowed in our languages, but we don't have a way to write what happens in response to those in a formal way. And having that would allow us to do lots of great things like prove that we have the right rendering. And I think that's also a really intriguing and important theory project to do.
Cool. There's a question from Cameron Yick on Slido now. It seems like the paper treats XML, JSON, and YAML as equivalent for purposes of analysis. Do you find meaningful differences between the different data serialization formats?
Not that I observed. There is XML ones are older. Just like XML used to be the workhorse of this style of language. Like during the DSL boom in the late 90s and early 2000s, that's how people wrote this kind of DSL. And we're in a different era now with JavaScript being a dominant language form. And so its native serialization format of JSON is prominent. And I think YAML is also cool, but I didn't see very many languages like that, but would like to.
Okay. Well, let's thank Andrew again. This is the end of the session. Thanks everybody for being here and participating.